want to be a know-it-all. I'm like, what?
Yeah.
What's that to do with anything? Anyways,
He's lied.
so, and I'll get back to your question, Silas. Metals, what can they do? You basically know all of this. Maybe you don't know this, but just from, again, living life, you know metals bend. You know they conduct heat and electricity. Not something you think of every day. It's not like when you cook something on a stove, you're like, they make this pot out of metal because it conducts heat and electricity. Ingenious. Like, no one thinks that, right? You're just like, all right, once it's ready, I'm hungry. But that's important. Know the properties. Why do they have the properties? There's really only one thing you need to remember, those mobile electrons, right? So why all of these? Due to the motion of the mobile, we'll just say electrons, in the crystal lattice. I want to use those words because I don't want you getting confused if you see them on a Regents or a test or something. Crystal lattice just means a repeating pattern. Like this room, the desks, they're in a crystal lattice. We talked about that word before. Lattice, like on decks or fences. Do you know what that looks like?
Yeah.
Lattice? Yeah. It's like kind of like crisscross, sort of.
Yeah.
Yeah. Anyways, if you know what I'm talking about, just imagine you had, like miles of that stuff. It's just repeating on and on and on. That's kind of what this looks like at the molecular level. There's like literally billions and trillions of these atoms arranged like that. So, due to the motion of mobile electrons, again, you apply force, they slide on the cations slide on those mobile electrons, and the reason electricity can travel is because the electrons are moving. When can electricity travel through ionic? Not as a solid,
In water.
in water, because the water allows the ions to move around. It's the same concept, just the bonding's different, okay? So when these start moving around in water, it conducts. Well, metals already have electrons. So in here, electrons are moving around. We can't see it. Obviously, it's at an atomic level. But that's really all we need to remember, okay? Now, what you asked, what is that called? When you mix metals? Alloys, right. Why do alloys exist, and what is an alloy? Make metal stronger, right. Good. Lights, please.
Brass.
Okay.
Oh, are you gonna do it? Are you gonna do it?
Maybe. I want to draw. Oh. I can do it. Yay! Some days I just don't want to.
But it always makes my day though.
Alright. I forgot I told you I'd give you a water bottle. Would you be willing to take one of my old ones?
Yeah, why not? I'll just wash it.
He's just gonna give you a dirty one with SpaghettiOs in it.
No, I have a nice one. I have a nice one.
Nice.
What's the answer?
Didn't read
First
it.
time buying it.
Hold it. Don't say it out loud. Don't say it out loud. I wanted to show you this because this is oddly familiar. We just did the like opener or warm up, whatever you want to call it. And the reason I had to do that, one, review yesterday, but two, this could be a Regents question. This is from June 2017, not that long ago. I personally like it when there's pictures, graphs, charts. Some kids don't, but you really should, because when they give you pictures, graphs, charts, the information's right there. It's not something you have to come out of your head. It's there. You just need to remember, okay, what does this picture have to do with it? So yes, it's coming from your head, but not the picture. So they're giving you more information than just a regular question. So, what's the answer? 1. Again, that's important to know the difference because they're trying to get you here. It's obviously not 3 or 2. 1, there's no hydrogen here. So if you were to put that, the test will literally grow a hand and slap you. Covalent, what do you need for covalent?
Metal and non-metal. Or
No,
two non-metal.
2 nonmetals, right. So again, that's how you eliminate them, but then it gets a little tricky because kids will say, all right, I remember they both have charges, positive, negative. You just need to remember the metals have the electrons. The ionic would look like that.
Is that usually on the Regents?
This picture, no,
I'm
but
not saying like that. but-
metallic bonding, yeah. There's always questions on covalent, ionic, metallics, pretty common. Yeah. That's why we spend time talking about the differences. Did everyone get the homework? I already sent the text out.
Wait, yeah, it's not home.
It's right here. This picture. I took a picture of this. I just made up questions. Just took. I just took. Well, I guess if I have to, yeah. I just took a picture of this and sent it. So if you don't have this, if you didn't get the text, I don't know. I'll leave it up here. You can come take a picture of it, or just that's due tomorrow. And I'm gonna collect it. I don't usually collect homework. I'm not gonna grade it like a test, but I just want to see. I want to see your thoughts and what you do. I just want to see it. So I'm still just gonna check it off as 100 if you do it. Anyways, yeah, this is metallic. Why? It has the electrons. Okay. All right. So we're done with that. I can't see. Okay. Here's pure metal. This is called a substitutional alloy. This is called an interstitial alloy, and this is both. You do not need to know this for the regents. You need to know alloys exist, that's about it. Okay, what is an alloy? It's when you take two or more elements, so it could be three. Like this one has three, red, green, and blue. Usually it's just two. Two different elements, mix them physically. It's not a chemical bond. So you're physically mixing them, and this is this alloy here is stronger, typically stronger than this one. Questions? You have
What's the difference between the inter?
that. I was just gonna ask you guys. Look at this picture and look at this picture. Hold on, just let everyone come up with their own answer here. What's the difference between this picture here and that picture? I don't really. That one up here, it's a good picture, but it should be. These blues should be a little bigger. The blue one should be a little bigger. Question? Or want to answer that?
Well,
Don't answer that.
I had a question.
Go ahead.
Which one is brass? Would it be interstitial?
I thought you just said grass. I'm like, well, we need to talk. Grass is not metallic. We'll talk about some examples.
And then,
All right, go ahead.
is there a way to like see just by looking at now which one it is? Or no?
Yeah.
So is it like only metals? In that?
No. In fact, a really, really, really common alloy, this green one, is a non-metal.
Wait,
Which I did not know until I started
then
teaching.
How is it an alloy?
I think
if
I know
it's a non-metal and a metal,
It's just the way it works.
it should be called
Is
an
it
alloy because
an
of metal.
ion?
Yeah, but
Alloy.
it's 96% metal, the red one, and 4% the green one. So
That's
it's
still dumb because it's still two.
you're right.
different-
It's just that's a dumb alloy.
Is it still a metallic bond then, or
The
does it have?
why? I don't like this.
I actually don't know the answer that you want, and I don't really know the answer I get. Why is that still called an alloy? Because it's basically all one metal with just a little bit of non-metal mixed in. I'll explain the difference. So who wants to tell me what's the difference here, and then I'll talk about it, and then we'll move on.
In the substitutional one, they're replacing the red ones, and the green one, they're replacing.
Right. So green, they're just going in between the space, like spaces between your desk. It's like bringing someone in or me, and I go stand between you guys. So or bring a whole bunch of students in and fill in the space between the rows. That's interstitial. Substitutional would be if I took 5 students from the hall, brought them in, and told 5 of you to leave, and they sit down in your seats. So that's switching. That's substitutional, like subbing in and out. Think of sports. You sub one subs in, one subs out, right? You're taking their place. Yeah.
So could an interstitial alloy being like if you put a metal into a cup of water and it starts like bubbling, releasing air bubbles, would that be like a interstitial?
Tyler,
No.
water is not a metal.
No. It's like within the metal though, and it would, like releases.
That's not gonna work. This you have to heat metals up and mix them so that they're pliable and that the atoms can move a little bit. It's not anything we can just like do. It's like a process, like melting iron ore and then
Right.
going from there. So I'm gonna try and explain it. Now, I'm not gonna pretend to know exactly how to make them. I just know the relative general concept of it. But I do know some examples. This interstitial is an example of the most common alloy.
Iron.
Steel. steel is made of iron, 96% iron, and there's different percentages. So don't quote me on that, and I'm being recorded, so I gotta, back myself up there. So, some steel is 96% Fe, and then, see this little diamond shape? Imagine you took 4 basketballs, 4 beach balls, or 4 fairly large spherical objects, put them together, there would be a diamond shape between them. Can you believe that? Can you imagine that or visualize it? You can see it here. We'll take a smaller, like, if you did that with basketballs, I don't know, maybe a baseball would fit, maybe not. But tennis ball, like something smaller goes in that space and it makes it a little bit more compact. So again, like putting people in between you guys, now the room is more packed and that's stronger because there's going to be stronger forces because there's less space. Less space means it's going to be a stronger substance. So guess what that element is? Carbon. Yep, it's carbon. So carbon is used for steel. Brass, and 3rd place in the Olympics. Bronze, that's substitution. Okay? Now, let me prove to you why this makes sense. Someone go to table S for me. Look up the radius of Fe, look up the radius of C. Iron, what's the radius of iron? What's the radius of carbon?
The radius of
124.
124?
Yeah.
Carbon is 75.
Right. Does that make sense?
Yeah.
Sorry.
That makes sense because iron is big, carbon is not half the size, but it's significantly smaller, so it fits. I can't take an atom the same size as iron and stick it between iron atoms. That's like taking 4 basketballs and taking a 5th one and smushing it in the space between the 4. That's impossible. Do you agree? Yes. Okay. I mean, as long as the basketball stays the normal
Sounds like a
shape.
challenge.
Inflated.
Right, inflated, right. So, we're not Tom Brady, Deflategate here.
Oh.
All right. Whatever. Whatever I say isn't affecting him. He's basically the best quarterback of all time.
Nope, nope,
I don't believe so either, but they're gonna say that.
nope.
All right. What about CU and ZN? Table S. Look those up, please. Somebody, I don't care. Anyway.
CU is 122.
Zinc is 120.
Yeah,
120. Okay. Does that make sense? Yes, it does for substitutional. Now, if I have 4 copper, but I take 1 copper out and replace it, if that's a zinc, basically zinc and copper are the same size. So I can just substitute in zinc for copper. So the structure of the lattice isn't going to change. Not really. They're both positive 2 as well. So that fits nice. That's what brass is. Copper and zinc is brass. Sterling silver, alloy. Gold, guess what? Alloy.
Wait.
All gold people wear is an alloy. Pure gold is 24 carats. 24 karat. So people who wear 14 karat, 18 karat, 10 karat, which is what most jewelry is, the price will decrease. So like 18 karat is more. If you have 2 rings, one's 18 karat, one's 10 karat, they're exact same size, weight, everything.
Don't get
10
them the
karat
same, too.
is going to be significantly cheaper. 24 is pure gold. 10 karat gold actually is 10 parts gold, 14 parts silver, copper, and other metals. So 10 karat gold is less gold and more other stuff. But it's much harder. It's also lighter. It's not as like yellow. Yeah.
Is it random? Like, the way they're arranged?
Oh, that's a good question. This is definitely not. I'm not sure about that. And I'm not sure how when people make, companies make alloys,
That-
the manufacturing of it, I'm not sure
Like
how
that's-
they would.
That's a specific arrangement?
They're going to want it to be, I think, fairly specific because that improves the strength of it. But again, that's just an educated guess. I would guess that is. I shouldn't say for sure because I really don't know. That's a good question.
What if you melted 2 metals and mixed them?
Right. Well, that's part of how alloys can be formed. So I don't. That's good. And like mix them perfectly.
Yes.
I think it depends on the size of the radius, probably how hot it is. Maybe pressure has to do with it too, and then different alloys. But I'm not completely sure. These are all good questions. Yeah.
Which is the strongest?
These are stronger than those.
But
Typically.
what about the combined?
Oh, you mean like this compared to this?
Yeah.
That's a good question. I don't know that either. Maybe it probably has to do with what they replace it with.
Okay.
I don't know. And then some are like stainless steel. Those alloys actually have an oxide layer on the outside, so it doesn't react with the elements. So it's got a protecting oxide layer. So those are kind of cool. We talk more about that in AP. Anyways, reagents, what do you need to know? Alloys exist. What is it? Basically mixing metals, mixing elements, and it makes the metal stronger. That's all you need to know. I'm not going to really give you any notes on it. Just know alloys exist, and it makes the metals essentially better. They're created to be more conductive or stronger or harder, and that's why alloys exist. All right. I want you to draw an ionic crystal in your notes. I think I got rid of them all. Oops, I just closed one. That stinks. Yeah. So just draw that. I want you to write ionic crystal, and the reason I'm having you draw it now is just, again, comparing the difference between metallic and ionic. So in your notes, just copy this down, and you can even label these Na plus, Cl minus, and I'm really kind of pounding this point home. I hope you're picking it up here. That ionic is very different than metallic as far as how it's put together. Yes, they both have positive and negative charges. Yes, they're both strong. Yes, they both have high melting points. They both can conduct electricity at certain points, but the way they're really put together is very different.
Is there any gases that conduct electricity?
Oh yeah, those gas discharge tubes. Those tubes, when we turn them on, those are gases in there, and they just electricity flowing right through them. Yep. Same concept. There's movement. Gas particles are moving, and they can conduct electricity because of that. Headlights in cars, light bulbs. The older ones are LEDs, but yeah, there's gas in them. Neon signs. Yeah.
So why, you know the tube with the metal rod at the end that you had that like sends electricity out of it, why doesn't it just connect to the air?
The air doesn't conduct very well. That's different than what's inside those gas tubes.
Okay.
The gas tubes are pure elements, and because they're under pressure, that's a great question. Because a lot of them are noble gases, hydrogen, oxygen. Actually, you know what? There is water vapor. So it has to do with 1, concentration, 2, pressure, and electricity. Here's the reason. What does electricity always try and do?
Take an electron.
Go down.
Ground. So that's why. It won't jump in the air because it's not going to get to the ground. So electricity always finds the quickest place to the ground. Right. So in those tubes, the quickest way is to go through the gas to the other side, and then it goes into the ground essentially. So that's ultimately why. So that's why. Okay, if I had that Tesla coil and I had a metal pipe or metal rod going straight into the ground, and I held it and went outside, it would arc if there was enough electricity. It would go through the air, hit the pole, and go into the ground. Does that make sense? So it's not going to just like electrify the air, and we're all just like easy.
Wait, what about like lightning?
Where's lightning coming from? And where's it going?
No. Like the lightning is like, it's just like all sorts of arc, and then it just goes.
Yeah, but it hits the ground, right?
Yeah,
Except
but
heat
why-
lightning doesn't, though. That's
Why-
interesting.
Yeah, but why doesn't like lightning just go straight to the ground?
That's a good question. I don't know. You guys ask me all these good questions today. Like, why does it kind of go?
Yeah, like why is it
I've never looked into that. I don't know. Good
I
question.
watched
It probably has to do with the air particles, the charges in the
Probably.
atmosphere, and the air affecting it. Because you can bend electricity, you know, like magnetic field type stuff. So maybe that's why. Just off the top of my head.
I saw this video of this dude, he had like a metal suit on, and he literally shot arcs of electricity at himself. Since the metal conducts better than him, it would go through the metal instead of him. Get straight
Yeah,
to the ground.
that's crazy stuff. That's kind of like the people who you could like dip your hand in water and then dip it in molten metal really quick and not burn your hand.
Oh,
we
you
talk
seen
about
the
that
video of
in
the
here?
guy like sticks his hand in ice and then slaps the molten lava.
Right, because it vaporizes the water in your hand fine, like that stuff. Theoretically, it's supposed to work, but I don't know. All right.
It's pretty cool.
The fourth type of bond, network solid. And this is what you need to know to finish that homework. So we got a little time, we're going to use it. All right, network solid. There's one example. What's that? Diamond. I'll give you the examples first before I give you the definition.
It's my middle name.
That's your middle name? That's a pretty cool middle name. Diamond. This is an example of a network solid. It looks very different than metallic and ionic. Very different. There's another way to see it. And there are three other types. Silicon dioxide, SiO2, silicon carbide, SiC, and graphite is another one. And then there's only two more I want to write, Si and Ge. Those two elements. They're called network solids. Now I'll tell you some of the properties. Network solids, so once you, sorry. SiO2 is called quartz. Earth is full of it. A lot of silicon and oxygen silicates on Earth. Si and O2, two of the most abundant elements on Earth. It's also the strongest material on Earth. That's what these are. I want you to write that. Network solids, the strongest material, strongest substances on Earth. That chunk, that rock back there that we smashed, which one's that? Silicon. Si. It's really.
Graphite's relatively.
Yeah, I'll talk about graphite. Hold on. Graphite's kind of like you just put a little star, you just put a little asterisk.
exception.
So it's part. No, it's part of the team here, but it's the weakest link. So.
What's the S? Of the
Oh,
bottom?
Si. Silicon. Now, here's what I need you to write. These are the strongest substances in the world, which means they have very high melting points. Diamond and quartz are two of the strongest things on the planet. Diamond-tipped drill bits, diamond-tipped saws. Maybe some of you have heard of that. It makes things very strong. Hardness in the earth science, remember that? How it resists scratching or how well it gets scratched. Quartz, really high, it's like a 7 or something on that scale, 6, 9, whatever it was, I don't know, pretty high. So, very high melting point, really strong, very hard. So it's kind of like metallic and ionic, like on steroids. It's like way stronger than that. Okay, they're strong, but these are stronger.
What's diamond company?
It actually doesn't melt, it vaporizes at 3,500 degrees Celsius, which is really hot. So that's pretty high. Here's why. Network solid have no forces of attraction. No forces of attraction. Oops, I'm supposed to be an A. All atoms are bonded to each other. All atoms are bonded to each other. And that's why I show you the pictures here. And I'll have to address the graphite tomorrow. But ionics, metallic, and covalent, all three of them have forces of attraction. And what does that mean? Well, if you take water, for example, if I have one water molecule and I have another water molecule and I have billions of them, then I can drink it. It's like in my water molecule. Well, this water molecule is attracted to this one because the hydrogen and the oxygen form this attractive force, kind of like gravity. But it's weak. It can break very easily. What can't break is the bonds. I use the analogy of shaking hands. This is a force of attraction. We can let go. The bonds would be what's holding my arms on my body. You've heard me say that a bunch of times this year. That's what I'm trying to explain. These guys here, network solids, they don't have these forces. It'd be like a stick going between this yellow and this red. All bonded together. So the pictures up here is to help you try and understand that. We haven't learned a lot about forces really. We will next. But these are all bonded. There are no forces. Metallic, ionic, and covalent have these things called weak forces. Since they have them, it makes them much weaker than network solid. So what do you need to know today about network solid? They're the strongest, and they have all bonds. If you can try and remember that, you're good. But don't worry, I'll review it again tomorrow. Yes?
Much stronger, diamond or artificial diamond, which is back to
Diamond.
Oh, yeah.
Actually, you know what? I'm saying that like I know for sure. I would guess it is, But if they can if they can make the cubic zirconium
Yeah, I read it.
perfect, maybe that would be. I thought you were talking about, there are diamonds that are grown in labs too, Victoria.
Yeah, no, I meant cubic zirconium. I didn't mean like.
Veronica,
Everyone.
sorry,
Why? What did you call it?
Victoria. In labs, there are scientists who can grow diamonds.
Like
If
real
you-
diamonds?
Yeah, if you can like
Di-
Google it, YouTube.
Diamonds aren't actually that rare, are they?
From what I understand, no. It's just how many are released onto the market.
Which
Kind of like a supply
Because if they
demand.
control it, then